Let's jump right into the urban landscape and learn about water quality concerns and ways that we can address them. So various water quality BMPs can be designed to reduce these water pollutants listed on the slide. Soil and sediment runoff, nutrients, again, primarily nitrogen and phosphorus is what we're concerned with. Various organic materials, including leaves, in the fall, oil, grease, and hydrocarbons, chemical pesticides and herbicides, bacteria and pathogens from sewage and other animal waste, and metals. They also help regulate stream flows and help slow runoff into the stream, which can reduce flooding impacts, and also can help improve riparian habitat, which we always like to bring up, and improve overall aesthetics by combating stream bank erosion, adding vegetation, and creating shade from stream canopies. There are endless resources available on this topic, including these 3 resources from Bowling Green, Louisville, and Lexington, all of which have very in-depth details on BMPs and how to install them. And so the information today is really just intended to touch on some of the most common practices and give you some kind of foundational awareness for your jobs, but we encourage you to take a look at these in the future if you need more detailed information. As there are a myriad of land uses in an urban landscape, there are also a whole host of contaminants and sources, and I'm not going to go through each of these individually. You have it printed on the slides, hopefully, or you can refer back to it. But this table just provides a nice overview of those urban contaminants and sources, from organic materials that I mentioned from residential lawns, or different contaminants from automobiles and impervious surfaces like roadways and parking lots, to the bacteria and nitrogen and phosphorus that can come from sanitary sewer line leaks or other animal wastes. Mantra in urban streamwater management, that is slow it, spread it, sink it. And you could also add a 4th S for settle it out, since pollutants are enabled to settle out in the different BMPs we'll be discussing today. Many of these that we talk about are tailored more for larger landscapes that handle bigger volumes of water, but this graphic here shows how they can be adapted to a homeowner's site, and they include ways to capture the runoff from the roof and impervious surfaces such as the driveway and sidewalks, and then spread it out and sink it into rain gardens and other landscape features in the lawn. You also may have heard about the gray to green infrastructure movement. And this is a description of the effort to transition away from traditional urban stormwater solutions to those that are based more on plants and using plants and soils to reduce stormwater pollution. Traditional gray infrastructure is designed to move water quickly away from the built environment, includes the curbs, gutters, piping, and systems that we've all become familiar with. Generally, the idea of these is to collect and convey stormwater from impervious surfaces and then direct them to the nearest water body. Whereas green infrastructure is designed to mimic nature, and it captures the rainwater where it falls and attempts to treat it in place, and has various economic, environmental, and community benefits, such as less damage from localized flooding, reduced construction costs and higher property values, environmental benefits of filtering pollutants, enabling better water quality, increasing groundwater recharge, and reducing greenhouse gases from the vegetation. And then also, I've mentioned improving water quality for public health perspective and creating more open spaces and and possibly also reducing the urban heat island effect. The fundamentals of green infrastructure include the means of capturing and temporarily storing the stormwater while it infiltrates and is taken up by plants or allowing it to evaporate. It also takes advantage of the natural abilities of the soil to support microbial breakdown of the pollutants. And practices generally prioritize native planting since they have higher transpiration rates, deeper root systems requiring less irrigation, and relatively low maintenance requirements. And these practices can be designed for targeted pollutants of concern and also create an attractive landscape design if well maintained. It's also worth reiterating the importance of the combined effect of reducing stormwater volume and pollutant concentration. Using these practices, as in this slide, the volume is reduced by half the concentration of the pollutant for an overall reduced total load of the pollutant of 75%. So you're having collaborative benefits, or sometimes called co-benefits, of these practices that help reduce the volume and the concentration, as well as the overall pollutant load, which is what we're trying to do. There are some drawbacks to going green. Those include maintenance. If they are not regularly maintained, they can lose some of their functionality. They can collect litter or debris that can clog the systems. And also there's some weeding involved in some of the vegetative practices. Some of the practices have more upfront costs, such as permeable pavement, so they can initially be more expensive, but hopefully pay off in the long run and require less additional practices in the treatment system. I mentioned some of the maintenance that touches on aesthetics as well. Some people are not as tolerant of some planted areas that may appear weedy, or some people may be fearful that they cause mosquito breeding, although that's proven to be largely untrue in most cases. And then also they can require larger areas of land, so sometimes it's a little more difficult to locate them in confined spaces. Okay, before I switch it over to Steve, and he's going to go into some of the specific structural BMPs, we just wanted to show this clip from a video that was made by Bluegrass Green Source, formerly known as Bluegrass Pride, and it provides a really good visual summary of what I've discussed, including the gray versus green infrastructure concept.
All right, for this portion of the presentation, I'm going to help walk us through some of the structural BMPs. BMPs can be categorized in many ways, one of which is whether they are structural or non-structural. Other comparisons are source controls versus treatment controls, point versus non-point source controls, but we're going to be considering stormwater BMPs according to whether they're structural or non-structural. The majority of BMPs we'll discuss in this module are structural practices, or built facilities that capture runoff, treat it, and then discharge it. These practices require construction, installation, and maintenance. Most non-structural BMPs relate to policy or educational initiatives to encourage human behaviors to minimize impacts. These can include erosion and sediment control planning and related ordinances, public information about fertilizer management, maybe pet waste pickup, or septic system care. Other non-structural measures are aimed at reducing imperviousness or connections to impervious areas and increasing open space and natural systems. During this presentation, we're going to be using a consistent format to describe each of the stormwater practices. The title will name the practice and label it as structural or non-structural. A short description with the pros and cons will be provided. The pollutants addressed will list the pollutants typically removed by the practice. And symbols are used for the relative ratings of low, medium, and high for their cost, the maintenance needs, and treatment effectiveness. We will begin with a review of several of the structural BMPs used to manage and treat stormwater runoff. Bioretention cells are the first structural BMP we're going to talk about. They can take many forms and are known by many different names. Rain gardens are often familiar to people, but they're also referred to as tree pits or curb extensions. These can be placed in parking lots, along roads, medians, or even offline from grassy swales. The name gives away how these practices function. They have bio, indicating that is biological microorganisms in the filter media that are working to achieve the water quality improvements, and retention, indicating that they hold water for a period of time. The filtration media of the bioretention cells help remove the pollutants, especially sediments and nitrogen, before the water percolates out of the retention cell. This process of using soil, plants, and associated microorganisms to remove pollutants is called bioremediation. The runoff flows into these areas through a pre-treatment area, often a forebay or a small depression, or maybe a graded entryway. The water then flows onto a soil media. A mixture of sand or gravel, soil, and mulch is planted with water-tolerant woody and herbaceous plants. This area maximizes infiltration and pollutant removal. The runoff is then temporarily stored in this area where it infiltrates into the soil. If the soil infiltration rate is too slow, an underdrain may be installed underneath and connected to the stormwater system. An overflow pipe and an emergency spillway is installed to allow for a bypass when capacity is exceeded. When these cells are created during construction, they are inexpensive and easy to install. They can be sized to suit many areas from suburban, commercial, and industrial settings, and can minimize the costs associated with curb and gutter or other stormwater drainage systems. This has a relative cost rating of medium maintenance, and medium effectiveness. Bioretention cells both reduce stormwater volumes and extend the duration of the stormwater discharge. By controlling these two hydraulic processes, peak flows of stormwater vents are reduced and the energy of the discharges are decreased. This slide shows several of the pros and cons of bioretention cells. They do have high pollutant removal of suspended solids, heavy metals, nutrients, and pathogens. They're very flexible in their use, and they can be put in the natural landscaping as well. Some of the cons are maintenance needs. The soil surface can clog over with time. It requires trash removal that may become unsightly as it flows in. They must be protected during construction activities, or else too much sediment will flow into the bioretention cells and run their function. And you may need to multiple them over a large drainage area in order to have some effectiveness. Here we can see some examples of bioretention cells. Both photos show bioretention cells that are in medians with curve inlets to allow for stormwater inflow. The photo on the left is from a parking lot. The photo of right being from a hospital in Maryland, courtesy of Ecological Landscape Alliance. The graphic shows the structure of a diagram of a bioretention cell. Here you can see the location of the media with the mulch, soil, sand, and gravel layers, and at the bottom, a perforated underdrain pipe with an overflow outlet. Rain gardens are simply a smaller bioretention cell that are vegetated depressions that store and treat runoff from nearby roofs, pavement, or other hard structures, typically around residences or small businesses. They're designed to accommodate the amount of stormwater you expect to capture and drain within 48 hours. The center of the rain garden should be planted with vegetation that can tolerate periodic ponded water or wet conditions. Sedges and rushes are usually ideal for these areas. As you move outward from the center, you can use plants that tolerate both wet and drier conditions. It is suggested that rain gardens should be planted at least 10 feet from the house and 40 feet from septic systems with steeper slopes. Weeding and watering are critical in the first few months of installation to help plants become established. Annual pruning and mulching are recommended, and some irrigation may be needed during drought periods. The use of native vegetation reduces maintenance needs, including the use of fertilizers and pesticides. Rain gardens are very similar to bioretention cells in the pros and cons. They reduce the stormwater volume and as well as their peak discharge. They can remove pollutants and they're very flexible. But the cons are they do need to be designed properly. They require some maintenance and buy-in from homeowners who have to be willing to install those on their private property. They also have limited impact unless they have really widespread use throughout a watershed area, a neighborhood, or a business district. Stormwater wetlands are constructed systems that mimic the functions of natural wetlands and use physical, chemical, and biological processes to treat stormwater pollution. In these wetlands, the microorganisms can eat the E. coli and other bacteria, and nitrogen is broken down by the anoxic conditions, and the phosphorus is taken up by the plant life. In this stormwater wetland example, the flow enters at the left side, flows into a forebay, which is a slow water pool area, where some of the sediments can settle out. It then flows through water levels of various heights to allow for different plants to grow. Some are submerged, some emergent, and some provide a variety of habitats and filtration through their dense root system. There's also a shallow micropool to provide some retention prior to flowing out of the stormwater wetland. There are also features such as a safety bench to maintain water within the feature and a primary outlet and emergency spillway to allow for a bypass when the capacity is reached. Other items that can be added to stormwater wetlands include trash rakes to remove some of the litter. A series of pools can be added to the wetland to increase habitat and variation. If you want to see an example of this practice, one place that you can go is McConnell Springs in Lexington, where you can see both a community feature and a water quality feature. Stormwater wetlands have medium cost, medium maintenance needs, and medium pollutant removal efficiency. And they can address sediment, suspended solids, metals, nutrients, pathogens, and temperature. Some of the pros of stormwater wetlands are just its power to remove pollutants. It's one of the best BMPs to remove sediment, nitrogen, and phosphorus, and also lower the volume. And it also can be very aesthetically pleasing, and it provides some great habitat for wildlife and wildfowl in particular, but other creatures as well. The cons is it can occupy more land than some of the other BMPs. The water level, the right elevation is very important. If it's too deep or if it goes dry, it's not going to function properly. So maintaining that critical water level is important. It can also be colonized by invasive species, so making sure that it's maintained to have a proper balance of native plants is important. And finally, due to the nutrient and sediment loading, it can create algae problems and the aesthetic problems associated with that. So we talked about stormwater wetlands, but floodplain, streamside, bankfull, or benchfull wetlands are just different names for the same type of feature. And so these are wetlands that are located in the floodplains or adjacent to streams. And so when water flows over the banks of the stream, it's stored in these wetlands for a prolonged period of time. This practice has a high potential to treat large volumes of polluted water by routing that overbank stream flows through these large offline wetland areas. Ideal candidates for the creation of bankfull wetlands include large, low-lying swaths of land adjacent to the channel and publicly owned lands. That'll help you increase the feasibility of getting it on the ground. The picture we show here is from the Gunpowder Creek watershed up in northern Kentucky at the YMCA Bankfull Wetland in Boone County. It's a 7-acre floodplain wetland, and it provides hydraulic restoration to the Gunpowder Creek while also improving habitat conditions, water quality benefits, and serving as an educational feature for the YMCA programming. Vegetated swales or bioswales can be thought of as a linear bioretention area. So think of an elongated rain garden. So these broad, shallow Natural or constructed channels have a dense stand of vegetation covering the slopes and the bottom of the channel. They could also include engineered soil or an underdrain system. So as the water travels along, it's being filtered out by the vegetation, filtering into the soil and reducing the pollutant load there. These have a relatively low cost in maintenance, but a lower overall effectiveness as they treat sediment, suspended solids, and nutrients. The pros of vegetated swales or bioswales is, well, one, that it reduced the use of more costly development and infrastructure such as curb and gutter or the pouring of concrete along a channel to line it. These can be quite aesthetically pleasing with the use of wildflowers. And they can even develop wetland areas if in low slope, flatter areas. They can also reduce the runoff velocity by creating a longer flow paths, and that vegetation channel roughness will tend to slow down the waters. Some of the cons may be that they can cause problems with the standing water and mosquito populations. They can also become channelized due to the concentration of flows within the channel, and then that can start the process of erosion. The low pollutant removal rates and the minimal volume control, just because you have less contact time with the media as it's flowing in it, so you're not getting the effectiveness that you might in other types of BMPs. But so because of that, these are often frequently used with other types of stormwater BMPs in a treatment train. Filtration devices or sand filters are a practice that temporarily stores and treats runoff through a filter media, that is sand, soil, gravel, peat, or compost. And then the water routes through an underdrain system into the stormwater pipes. These can be effective in treating runoff from small, highly impervious sites at medium cost, maintenance, and effectiveness. Primarily, you're looking at treating nutrients in this case. These are not effective in reducing runoff volumes, and they are not applicable for use in karst areas due to the potential for underground misrouting into nearby waterways or aquifers. We now want to look at two different structural practices that are often confused because they have very similar sounding names. That is the retention basin and the detention basin. The retention basin is also known as a stormwater pond or a wet pond, and it's designed to maintain a permanent pool. It does provide some extra storage, but the pool is going to be there constantly. And the goal is that the pollution that flows into that will be treated through biological uptake, so primarily addressing nutrients and sediment via a retention basin. A detention basin is going to be dry for most of the time. So it's designed to detain stormwater for just a couple of days to reduce that peak flow and to settle out the pollutants. You're not going to see a maintained pool between stormwater events. You may see some wetland vegetation or shallow pools develop at the bottom of the basin, but otherwise it will be dry. So to provide a little bit more detail, wet retention basins, those that have a pool in the bottom of it, they're designed at treating water quality, especially suspended solids, nutrients. They will provide some value in reducing the runoff volume as well, as there's some capacity in these systems. So they should include a forebay area that traps that coarse sediment and eases the maintenance procedures, or else they'll have to be dredged periodically. The perimeter should be covered by dense emergent wetland vegetation. They require adequate inflow to maintain that permanent pool, and that's why they're called stormwater ponds, because the stormwater is flowing into them and refilling them over time. Pros of retention basement is the treatment of water quality. A lot of subdivisions like these just because the look of them. They may put a fountain in there, so they provide recreational as well as wildlife benefits. You may see a lot of wildfowl in the area. They also capture some of the stormwater volumes, and so they limit the impact, and they can be designed to control peak flows. Some of the cons is that the ponded water can be viewed as a safety concern, especially if there's young ones in the area who may wander in there. The maintenance and sediment removal can be more difficult within dry basins. Again, if you don't have a forebay there that can be cleaned out regularly, you may be talking about dredging. And then there's other maintenance concerns such as floating litter, algae or scum, maybe there's odors from it, or aquatic plants. It does require a permanent pool, which may be difficult to maintain if there's not sufficient drainage. And they can attract a lot of geese, which can add to the nutrient and fecal loading around these basins. Now, that being said, if you allow vegetation to grow up that blocks kind of the line of sight of these geese or wildfowl, then you can reduce that factor. Dry detention basins are simply surface depressions, or think of them as large bowls that provide temporary storage of the stormwater runoff. They release the flow slowly over a period of a few days and are normally dry between events. They represent one of the most common stormwater BMPs since the 1970s and have helped control runoff peaks as well as providing some reduction of suspended solids. Some of the pros are just the simplicity of design, makes them relatively easy and inexpensive to construct. They can capture some sediment and pollutants as they settle out. They reduce the volume of the runoff, which is their main. So you're looking at water quantity concerns here, having a bowl to hold the water to slow it down and release over time. And they can be designed to provide other benefits, such as recreation and open space, which we'll look at momentarily. Some of the cons is that they do require quite a bit of flat land. They only have moderate pollutant removal as compared to some of the other structural practices, and they're relatively ineffective at removing soluble pollutants. They do have the potential for clogging with perhaps leaves or logs or those types of things when they flow in and block the outlet. And they can detract from nearby home values because of the large expanse of dry, bare area with inlet and outlet structures. So there has been a push to retrofit old detention basins that were designed mainly for flood prevention. And so these retrofits can improve the overall effectiveness of treating both volume and pollutant levels. The speed of the stormwater movement through the basin channel carried trash, sediments, and pollutants quickly through the channel. Turfgraphs did little to slow movement and was not effective at soaking up or filtering the stormwater. Additional water entered the basins at its edges, and the outlets were designed to move water out of the basin quickly into the receiving streams, causing erosion and water quality problems. A retrofit of a dry basin can better enable natural processes to help stormwater soak into the ground and re-enter the atmosphere. So these retrofits can include a forebay that slows down the stormwater as it enters in through the outlet, allowing some of the sediment to settle out, a berm or an energy dissipator that forces the water to disperse to the sides of it, and that would slow it down and spread out the flow. There can be added meanders to the flow path to further slow down the water and spread it out. Additional plantings can help absorb some of the water and encourage it to soak into the ground. Possibly a rain garden pocket that provides a concentrated area of stormwater treatment can be added. And the outlet and outflow structures can better be used to control the amount and the timing of the water releases. Okay, moving away from the basins, we want to look at underground detention. So underground detention is a practice for collecting and detaining stormwater runoff underground in a system of pipes, vaults, chambers, or modular structures. This water is then released back into surface systems at a reduced rate. So the idea here is that you're not losing some of the valuable land on the surface, but you're capturing it underground. In these systems, they're typically made of concrete, steel, or plastic. When water quality improvements are needed, they should be used in conjunction with other practices or pre-treatment devices. These are primarily addressing water quantity. Underground detention structures are typically seen as a preferable option in areas that are highly developed and land is at a premium. So maybe a residential, commercial, or industrial area in which putting a parking lot on the land with underground detention would be a better use than putting in a large detention basin or something like that. These structures need to be constructed so that gravity helps water flow into and out of the system with a slope of no more than 2%. They should be located in areas that can be excavated if needed for maintenance or repairs. Installation of some sort of access hatch for maintenance is important. Another structural practice that's frequently used in stormwater areas to address primarily litter, but also some oil and grease and floatables, are catch basin inserts. So these inserts are installed under stormwater grates or inlets, and they do catch sediment, debris, oils, and metals, things that are running off in that stormwater before they go into the stormwater system and end up in the stream. Catch basin inserts are easy to install in new construction or to retrofit in existing construction. They work great in a treatment train approach, and you can put them in a lot of situations. But if you're getting a lot of pop bottles, plastics, floatables in an area, this is not going to address your flow concerns, your water quantity, but will help with your water quality. They're not going to be effective for pollution treatment like nutrients or something like that. It also doesn't address the dissolved pollutants or fine particles. They do have to be upkept, so there's going to be regular, maybe monthly or weekly, depending on how heavy use the area is, but there is going to be regular maintenance to go out and dump these, or else you're going to have overflows of your stormwater system because their inlet is blocked. And if you are having high inflow, like during heavy rain or flood events, you may have to do maintenance more frequently. But if you don't mind doing the maintenance, this is a great solution. Manufactured water quality units are built into that gray system, kind of like the catch basin inserts are, to provide water quality improvements within it, typically near stormwater inlets. So these are installed underground, and they often enable a swirling motion that helps remove sediments and particulates that settle out. They can have chambers that capture floatables such as oil and grease. So these are maybe a little bit more expensive, but very effective at capturing sediments and floatables and litter as well. The pros: easy to install. These can be put into existing infrastructure, and it can be optimal for sites that don't have the space to accommodate some other green infrastructure practices. These are not going to address volume reduction, so you're just going to have water quality treatment. You're going to have different amounts of maintenance frequency. Often you have to move a Vactor truck up to these to vacuum them out, so they need to be installed in a place where you can access them. Again, this is not going to address dissolved pollutants or fine particulates, and they can be a source of pollutants if not maintained adequately. That is, bacteria can grow on top of some of these surfaces, and so it can contribute to some of the bacteria base loading. Restored riparian buffers are one of the best structural practices no matter the land use situations. So in agricultural, mining, or urban situations, as we're talking about here, riparian buffers are great. So these are vegetated zones along the streams or river banks. That could be a variety of widths. We'd like to see a minimum width of 50 feet to provide all of their full benefits, but even some buffer is better than no buffer. Riparian buffers provide water quality treatment because they reduce the flow as it flows over the land surface and into the water body. It also helps control erosion. The shading can lower the temperature. It can help armor the stream bank against erosion, and it provides aesthetic and passive recreational benefits, as well as wildlife habitat for the many creatures that like to live along stream banks. The cons are that some view these as unkempt areas, depending on the way that they're managed. You can have wild insides and and kept outsides, but there is a perception in some cases that these are unkempt or weedy areas. They can be perceived as obstructing views of stream, especially with the scrubby vegetation, and they can be abused as places for dumping trash or litter. Porous pavement or permeable pavement is available in many different forms, but it's an alternative to conventional paving materials such as concrete and asphalt that allows stormwater to infiltrate into the void spaces. The common use for permeable pavement of its different forms are parking lots, sidewalks, and multi-use paths. Stormwater can infiltrate the soil or be detained underground and then released. Options include permeable pavers, porous asphalt, pervious concrete, or reinforced turf. Permeable pavers create hard surfaces that allow infiltration of the stormwater through gaps between the paving components. They can be used in block or grid systems and are aesthetically pleasing. They are also compliant with the Americans with Disabilities regulation. Pervious concrete is a permeable pavement that allows water to infiltrate into the subsoil through the pavement surface and base layers. It is designed without any fine material, resulting in a mixture that has large void spaces. Pervious concrete should be used over soils that allow sufficient infiltration rates. Louisville Stormwater BMP Manual recommends subsoils with a permeability of at least 0.5 inches per hour. Porous asphalt allows water to infiltrate into the subsoil through the pavement surface and a stone reservoir. It is developed with a single aggregate size that allows for gap-graded mixture and high void space. In addition to the subsoil requirements for pervious concrete, it is important to assure that the high water table is at least 3 feet below the subsoil's surface. Permeable pavement allows for stormwater to infiltrate or to be detained as it flows over its surface. These are often advertised as reducing the need for application of salt on parking lots. It eliminates the standing water that's there and reduces the pollutant loading and runoff rate and volume because of it. It also reduces the land consumption by providing that infiltration there rather than having offline structures such as a detention basin. So this can be a very attractive pavement option, but it's going to be probably more expensive. It can also become clogged with sediment without proper maintenance or construction staging. And that sediment will reduce its effectiveness. And often if it does become clogged, there's specialized equipment that's needed to vacuum out these pavements on a regular basis or interval. This is not applicable for all site conditions, such as in roadways or under a tree canopy, which can cause excessive clogging from the fallen leaves. And again, it is going to be a much higher cost than conventional options, and so but it may offset because you don't have to install some of the other stormwater Bs on the grounds. A great way to involve the community in water quality improvement is through rainwater harvesting via rain barrels or cisterns. Rain barrels or cisterns work by capturing runoff through the gutter systems of the roof and directing them into temporary storage tanks that can be released later to use for watering gutters or other uses. Widespread use in an urban area could help reduce runoff volumes and subsequent pollutant loading from the runoff itself. These practices do not capture and treat pollutants, but they just are meant to capture and prevent stormwater runoff from continuing off-site. So they just slow it down. If the water is not used for beneficial purposes such as watering plants or washing cars, or gradually released between storms, then it really doesn't provide any benefit at all, because it's just bypassing this and it's functioning essentially like a gutter and otherwise. But captured rainwater can be used for many different purposes. Advantages of rain barrels are that they take up little space, they're inexpensive, and they're easy to install. Mesh screens can be uh, placed into the rain barrel to prevent debris from clogging the barrel's faucet and from mosquitoes breeding. They can also use natural mosquito dunks to prevent mosquito larvae from hatching there. Emptying rain barrels no more than a week after the rain event will help prevent the water from becoming stagnant. If used properly, rain barrels or cisterns can enable sustainable use of stormwater, reducing water bills. This includes some businesses have used these and repurposed for toilet flushing. Schools have installed large cisterns in order to irrigate some of their athletic fields, and so these can provide an effective means for reducing the water bill. Also, because they're reducing the flow, if it's captured and released over time, then they can reduce those peak flows and the energy of that stormwater, so that reduces the volume and that erosional force. And of course, you got that beneficial reuse of the stormwater. The cons is that they do need to be drained regularly between events. Overflow needs to be routed to a stable pervious location, so when it is being bypassed, it's still going to flow into the ground and not on a concrete surface. These are not ideal for use with tar, gravel, or asbestos shingled roofs because of parts of those roofs will come off during the rain events and collect in the rain barrels. And you may need to use some deterrent for mosquitoes. The last structural practice that we'll mention is the green roof or the vegetated roof. A major benefit of a green rooftop is their ability to absorb the stormwater and release it over a prolonged time period. They have been shown to retain 60 to 100% of the stormwater received. The roofing system is made up of multiple layers, including a waterproof layer to protect the roof or drainage system, engineered soils, and vegetation. Extensive green roofs have a soil layer of 6 inches or less that supports dense, low-growing, drought-tolerant plants. Intensive green roofs have deeper soils greater than 6 inches in depth that can support larger plants, shrubs, and trees. The selection of the soil material will affect the quality of the effluent from a vegetated roof. Typically, non-organic, high mineral content soils are recommended. Vegetated roofs can prolong the roof's lifespan by protecting the roof from ultraviolet radiation and extreme temperature fluctuations. Green roofs can increase nutrient runoff due to the nutrients present in the soil. For this reason, typically non-organic, high mineral content soils are recommended. Also, if birds and other wildlife are attracted to the roof, they can be a source for bacteria runoff. But green roofs can, again, reduce the runoff volume, reduce some of the pollutant concentrations of conventional roofs. They add landscaping value, aesthetic value to the rooftop while decreasing cost. But it does require adequate roof structural support and a mineral roof slope. We're talking about a flat roof that's there in order to support that additional weight. The plants that are being used on these rooftops are going to be very drought tolerant. You can think about the temperature of the roof and the extreme sun and wind conditions that they receive. There also is some potential for roof leaks, and oftentimes because of that extreme heat, irrigation is required to make sure that the plants are established and maintained. So there's a cost for the watering of these green roofs.
Okay, so now I'm going to address the urban non-structural BMPs. These are the ones that focus on educational or policy approaches to helping change behaviors in ways that limit runoff pollution in urban areas. Due to the broad community audience and the huge range of stormwater runoff sources, public education is critical and ongoing. Raising awareness about stormwater pollution and all the different contributors is critical to achieving success. In this example, a simple educational campaign is being used to address or to illustrate how homeowners should responsibly get rid of their leaves in the fall, suggesting either putting it on the curb for city pickup or composting it, rather than in the street where it can block the storm drains and cause backups, or in the creek where it can harm aquatic life. Also, most people don't know that stormwater captured in the storm sewer infrastructure is directed straight to a natural water body without being pre-treated. Thus, things like storm drain stenciling campaigns are a way that you can help educate people about this fact and help them understand that dumping down the storm drain is effectively dumping it into the stream. This photo in the bottom right was taken from Bluegrass Green Source's website. If you're not familiar with this organization, they help do a whole host of environmental outreach programs, one of which is helping local communities organize storm drain stenciling efforts. There are many education and outreach resources available from all kinds of organizations and government agencies online. One of the most effective campaigns is from the Chesapeake Bay area. This rainscaping poster shows the concepts of green infrastructure and how it reduces runoff pollution. Rainscaping suggests simple measures for reducing the stormwater runoff, promoting infiltration, and filtering runoff by controlling it at its source through some of the measures we've already talked about today. They also have information on the more complex and larger scale measures in addition to those for homeowners. Urban behavioral management focuses on promoting practices among local residents that benefit water quality. Widespread adoption of these practices can have a large impact because, well, collective impact the more people that implement them. However, it can be difficult to convince people to change their habits and behaviors through messaging alone. So it's good to find effective incentives or alert people to associated cost savings to help motivate them. For example, lawn fertilizer application. Obviously, when people over-apply fertilizer or apply it at the wrong times, the nutrients in the fertilizers can wash off into streams and cause water quality problems. So it's helpful to provide education about the appropriate amounts, the timing, and the frequency for lawn fertilization. And this may include getting free soil samples evaluated at county extension offices to help them fine-tune their fertilizer needs and maybe help them realize that in many cases in Kentucky, additional phosphorus is not needed due to the high levels already present in our soils. When yard trimmings are left in place and are vulnerable to storm runoff, they can also wash into storm drains and local streams and become water quality problems. Composting is an option that allows it to become a valuable organic fertilizer for your gardens and lawns. Additionally, by picking up pet waste and disposing of it in trash cans, people can reduce the amount that washes down storm drains and into waterways. This eliminates the additional nutrients, bacteria, and organic matter that reaches the streams and other water bodies. And public awareness campaigns combined with convenient pet waste stations can help encourage this practice. Car detergents can contain high levels of phosphates and other nutrients and soap suds that can harm aquatic life. So rather than washing cars in driveways where they can run off, where the substances can run off to the nearest water body, we encourage people to use car washes or wash it on grassed areas instead of their driveways. Conservation watering is a way to prevent overwatering of lawns that creates unnecessary runoff. And in this practice, we encourage efficient landscaping using some of the native plants and grasses that we've mentioned that require less irrigation. And then finally, downspout redirection refers to the disconnection of the gutter downspout from a pipe or paved area and redirecting it to either a lawn or garden or the rain barrel that Steve previously mentioned. And this helps reduce the amount of runoff from the property. A different type of non-structural BMP is a policy to reduce the requirement for curb and gutter systems and instead create curb cuts in inlets where the yellow arrow indicates that go into maybe a planted area with the tree where the water can infiltrate. That photo on the right also shows a crosswalk that used permeable pavers to allow for additional stormwater infiltration. Street sweeping is another practice that helps remove larger debris and some particulate pollutants from roadways and prevents them from entering the storm sewers. With proper equipment and program design and scheduling, street sweeping can significantly reduce total pollutant contributions. And sometimes parking prohibitions and other program factors can further enhance this BMP's performance. Steve also touched on the large numbers of waterfowl that can be attracted to some of these wet basins or retention basins. And those waterfowl in turn can add nutrients and bacteria from their waste. And so there may be added controls needed to reduce the numbers of waterfowls that congregate in these areas, such as maintaining tall shoreline vegetation and that might require no-mow zones around the areas. Addling eggs, which is something I had to look up. The Humane Society even provides guidance on how to make the eggs non-viable to reduce populations through either coating them with oil or just removing them. You can also introduce predators, which might not be so popular in urbanized areas, and then just simply stop feeding them, which is often easier said than done. The use of road salts for safe winter driving conditions can also raise the levels of chlorides and salinity in surface and groundwater and potentially harm aquatic life. In some of the practices that help reduce this threat are training local municipal road crews on how to calibrate the equipment for salt application and monitoring the amount applied to reduce things like is what's happening in the photo on this slide, where we get large clumps of salt that are likely to run off. Also, properly storing the de-icers and road salt so there's less likely to run off, and then maybe using other de-icing solutions such as abrasives or a brine solution, and then snow fences, which luckily we don't have to worry too much about heavy snows in our area. These and the other like municipal stormwater management needs are addressed in stormwater permits, which are required by many communities by the Kentucky Division of Water. And this refers to the MS4 permits that we've talked about previously. MS4 standing for Municipal Storm Sewer, sorry, I always mess this up, Separate Storm Sewer System permits. And included on these permits are 6 minimum control measures, each of which are worthy of a separate discussion. Well, we just wanted to make sure you're aware of these requirements for many of the communities in Kentucky with significant populations. MCMs 1 and 2 relate to much of the work that we do as watershed coordinators on a regular basis to make sure that people are aware of runoff impacts and many of the BMPs that we've described today. And municipalities with these permits are also required to do this. Illicit discharge detection and elimination addresses the need to find and remove dry weather discharges to storm sewer systems. These can include illegal wastewater connections from homes or businesses, and improper disposals of wastes into storm drains. MCM4 relates to construction site stormwater runoff controls that mainly address soil and sediment pollution, and we're going to spend a little more time on this in the upcoming slides. MCM5 relates to post-construction in new development and redevelopment in areas that disturb an acre or greater, or smaller lot sizes that are part of a larger development project. And finally, MCM6 is similar to what we were just discussing with relation to the road salt de-icers. It requires permittees to implement an operations and maintenance program to prevent or reduce polluted runoff from the municipal operations. So I just wanted to go a little bit more into the MCM4 for erosion and sediment control. A very good guidance document for this measure was created way back in 2001 through a 319 grant from the US EPA. And this guide outlines many of the pre-project planning and operational activities and then related erosion control measures that should be utilized in these stormwater communities. And by paying attention to the construction-related activities in the yellow box that really do aggravate erosion, it's easier to understand what is needed to help with erosion prevention. Basically, you just need to try to avoid or do the opposite of these things listed here, from removing vegetation and topsoil and organic matter. It relates to the way the land is reshaped and the subsoil is exposed to precipitation. This graphic shows the basic concepts that are described in the manual that address those issues that I just mentioned. The practices follow a top-down approach from higher levels above the construction site and proceed down the slope all the way down to the nearest water body. Instead of removing vegetation, you want to try to preserve it as much as you can, especially near water bodies. And then also seed and mulch bare soil as quickly as possible. When bare soil must be exposed and left that way, it's best to divert upland runoff around it through possibly a berm, creating a berm around it. And then also using sediment barriers to prevent soil from running off of the construction site, such as the silt fence used here. And protecting slopes from gully formation. Here, I believe they're using an erosion control mat to do that. And then also using sediment traps and settling basins to catch soil that does escape the site. So the publication begins with these introductory concepts and then provides much more detailed guidance on ways to reduce these sources. A course on the topic of erosion and control. Erosion and sediment control is really worth a whole day in itself, but we wanted you to at least be familiar with these basic concepts and the different stages, all the way from the planning phase to the construction phase to the site closure phase. You're definitely encouraged to look more at the publication, and the website is listed at the bottom of the page. The publication includes really good graphics as well as photos with thumbs up or thumbs down to show good examples and poor examples. For instance, a lot of guidance and examples are provided for the installation and maintenance of silt fences and other silt barrier methods, such as the straw bales that you can see here. In the poor example, you can see that the developer hasn't really done a very effective job of keeping soil on the construction site. The straw bales and the silt fencing are failing, allowing soil to escape onto the roadway, and the stormwater inlet along the curb is not protected from soil entering. It is noted that the site also has a is a good example of proper seeding and getting a good protective cover of grass in place on some of the exposed areas. Once the construction phase is complete, temporary controls such as those sediment fences can be removed, but some of the permanent erosion controls will need to be inspected and maintained for future effectiveness. Permanent violations or other legal liabilities can result if some of these practices are not properly left in place. And the KPDES permit will provide a complete list of closeout requirements that the developer must follow. Moving on to another general non-structural BMP, land protection approaches can be used to identify, map, and prioritize key features listed, such as those listed here: floodplains, wetlands, riparian areas, drainage ways, and steep slopes with highly erodible soils, all of which can have really important functional value in helping address stormwater. In this approach, community planners and leaders can help protect these features from future development, possibly with local ordinances or by purchasing the land and attaching conservation easements. This preventative approach can greatly enhance both water quantity and quality management. This photo shows an example in Lexington of their greenways program that's created and managed by the city. And these serve as corridors for wildlife and people and often include recreational trails. Some of them are designated as conservation greenways with the primary purpose of providing water quality and wildlife benefits. And private landowners that border these greenways are instructed not to mow them or alter them. And then if they want to put any kind of structures in the space, they need to apply to the city for a special encroachment permit. Finally, the last practice that's to be covered today is conservation design development. These sustainable development approaches are promoted to encourage economic growth while also protecting the natural environment, including water. The Center for Watershed Protection has developed a really helpful Better Site Design Handbook that includes model development principles. And these overarching goals of these are to reduce impervious cover, conserve the natural areas, and reduce stormwater pollution from new development, as well as lowering the overall development cost and hopefully enhancing the quality of life in these neighborhoods and creating some more open space for recreation, safer streets, and a sense of community. And the principles apply to what the center refers to as the 3 habitats of the suburban landscape. Those are residential streets and parking lots, or the habitat for automobiles. Lot development, which applies to habitat for where people live and work. These principles focus on things like lot size and shape, housing density, and the overall design of the neighborhoods. The example on the slide shows a development in Maryland. It's a conservation subdivision with condensed housing and large open spaces and fewer roadways. And then also the natural area obviously is a habitat for wildlife. So that relates to that preservation of the open spaces. Unfortunately, many local codes and ordinances actually work against or even prohibit these approaches, such as requiring unnecessarily wide residential streets, expansive parking lots, curb and gutter roadsides, or the clearing and grading of large areas of land. And so the Center for Watershed Protection has developed very detailed guidance and worksheets and other tools that can help communities work through some of the existing development requirements and hopefully better tailor them in ways that allow and maybe even encourage some of these smarter, more protective development practices. Okay, now we're going to open it for any, oh, sorry, I have one final slide that that you'll have in your printout of references and resources, including that link to the video that may or may not have come through for you. So we'll open it up to any more questions and comments that you might have.